All right, so it's my pleasure to have Surya here to give us a wonderful talk on power quality data analytics. So Surya got his PhD from UT Austin. So after practicing his knowledge in the industrial, he actually went back to UT Austin to be a professor. He's a fellow IEEE, and from my past knowledge, he's one of the guru in the power quality domain. So today we are very happy for him to be here, give us many practical situations and solutions for power quality related problem. So without delay, I will pass this microphone to you. Thank you.
Okay, thank you, Dr. Yang and Dr. Wang, and thank you everyone for being here early this morning. I realize this is early, 10 o'clock, probably not student times yet, okay? But nonetheless, I'm also glad to be around here in Arizona State in Phoenix. I found that the weather is really, really hot, like early in the morning, okay? But what I'd like to do is to share with you some of our research outcomes, particularly on data analytics, okay, power quality data analytics. I've been working in this area on and off for over 25 years, so it's been a long time. Back then when I started, okay, and this was actually part of my PhD topic, it was not called data analytics. Instead, it was simply called automated data analysis, okay? But I believe that the objective of the work remained essentially the same. That is that we have a lot of power quality data that has been collected elsewhere. And then what we try to do is to convert the data into knowledge. And this knowledge is something that is useful for utility operations to improve the power quality or to catch impending failures, okay, or incipient faults like that. And I'm particularly grateful that most of our work in data analytics has been supported by utility companies across the US. First, they provide, of course, funding, and then they also provided data, which I really appreciate. But most importantly, I don't know.
It's on.
Yeah.
Here.
Yeah.
Okay. And then most importantly, they also provide their time and expertise. They want to talk to me, and then in fact they teach me how to analyze power quality data, okay? So therefore in developing the analytics, okay, the algorithms that I develop is very much influenced by the way I learn things from power engineers, okay? So what I have been trying to do over the past 10-15 years is always try to mimic the thought process of engineers, okay? So, first, I try to learn how they think and codify the way they think and put it in a more systematic algorithms like that. Okay, so in the next hour, okay, what I'll do is first to show you some examples of disturbance waveforms. Okay, and then I'm going to show you instrumentation and locations and the data size just to give you some idea. And then I'm going to show some general approach on how I develop the algorithm. So I'm not going into the specific details, but rather give you the broad pictures, and then you can fill in the blank on your own, okay? And then I'm going to show applications, particularly on capacitor health condition monitoring and incipient cable fault detection and locations, okay? So I think, okay, so this is the some example waveforms of disturbance, of power quality disturbance. You can see that in here, this is a reference waveforms. That is a perfectly sinusoidal waveforms, where you can see that the voltage magnitude is essentially at the nominal. And then you also see that the frequency here is essentially steady at 60 Hertz. And then most importantly is the wave shape. You can see the wave shape as well. Now compare that reference waveform with these other waveforms. All of these are what we call the voltage waveforms. Of course, they are voltage waveforms, they are current waveforms. But what I'm showing you here are simply the voltage waveform. You can see that this one in here, initially in the first cycle, Also, it is a perfect sinusoidal, and then you can see that there is some kind of transient event, and then following the transient event, you can see that there is a harmonic distortions. Okay, so if you have a look into some of these waveform, you'll recognize this has mainly have to do with the transformer being energized. Okay, now and then you can see that in this one too, that the waveform is initially smooth and nice, and then you see some transients, and then you can see also some big spike, although we should not call this spike. Okay, and this has to do with capacitor being taken out of line, okay, out of surface, but then it restrikes. Okay, a capacitor de-energizing is supposed to be very smooth, and you should not see much transients. Okay, but this one you will see that this is like in the first few cycles, the waveform is smooth and normal, but then due to some system conditions, okay, then it goes into what we call dynamic overvoltage. Okay, so all of these are just small examples, textbook examples of disturbance waveforms. Okay, and then all of this in here, the term that what we usually call this are what we call wave shape fault. So the wave shape has a fault. Okay, it does not necessarily mean that those are short circuit, but it's simply that the shape itself has a fault. Yes, Ramesh.
So are these all taken from real data?
Yes, all of these are real data. I call this still textbook example because it is so nice and so clean. Okay, but this is actually taken from utility measurement. And in fact, all the waveform that I'm showing you are taken from real world measurement. Okay. Now, where are these disturbance waveform captured? Okay, first they are captured using power quality monitors, which I will show you a little bit later. But in here, you are familiar that all of this, this is essentially a distribution feeder. So what you're looking at, this one of 4 feeders in here, and then you have a normally open switch in here, breaker, and then it's supplied by a distribution transformer, and then this distribution transformer is fed by 138 kV transmission lines. Okay, so power quality monitors can be located anywhere, practically what you like, but typically it is located right here at the feeder head. Okay, so if you have a power quality monitor at this position in here, it means that this power quality monitor is going to see all the currents that is flowing into here. So whenever a load is energized, you will see it. When a capacitor energized, you will see it. When a squirrel touches the line, you will also see it. Okay, and so on, it will see everything. Okay, now whether that is a good thing or that is a bad thing depends on what you want to do with the data. Okay, and then so this PQM3 only sees the current downstream from here. Now, if you place it right here, then you will see all the currents going into each feeders, going this one, this one, this one, this one, combine all of them together. And then you can even capture a lot more data, a lot more disturbances. Again, whether it's a good thing or it's not a good thing, really depends on what you want to do. Okay, and then you can also put your power quality monitors just at the terminal of the device that you are trying to evaluate. Okay, in this case, perhaps you want to assess the health condition of the capacitor, so you put it right there. So all the currents that you see are all capacitive current. There is no other current, not supposed to be. Okay, so whether there is a energizing or de-energizing, it must have to do with capacitors. Okay, now now the next thing in here, okay, so this is instrumentation, power quality monitoring. Okay, when you think about power quality monitors before, way before 95, early in the 90s, we don't really have power quality monitors. So you can think power quality monitors are essentially utility scale, utility size oscilloscope. Okay, oscilloscope that you put in on the distribution transmission to get the waveforms. Okay, now there are 2 basic kinds. Okay, one is what we call the continuous data recorder. Okay, so it will record waveforms or RMS values or whatever continuously, regardless whether there is a disturbance in on the line or not. It is just keep eating up all the waveform that comes around. So at the end, you end up with tons of data, so much of the data. Okay, so the headache is that you have too much data, but the good thing is that it will capture everything, good or bad. Okay, whether you want it, you don't want it, it captures everything. And then at the end, when it arrives in your computer, then you have to sort through what are you trying to find. Okay. Now, whereas this one in here, this is called the Disturbance Monitor. It will only capture disturbances. Okay. So inside this disturbance monitor, there is an algorithm already living there that is keep watching on the wave shape. Okay. And then when the wave shape or the amplitude exceeds some threshold, it will trigger a snapshot. Okay, a snapshot is basically like 2 cycles before and maybe 10 cycles after. Typically, it's like that. And then so this is very handy, very useful in the sense that the data that you capture have to do with disturbance, some form of disturbance, some kind of disturbance. Okay, but then the problem is that you may be missing out on some data. Okay, sometimes you don't know what you are missing. So are you ready for that? If you are good for that, then it might be okay. All right. Now the next thing is that how they are triggered. Okay, these power quality monitors. So these are some of the most basic one. Okay, you can have even more advanced signal processing technique to develop this kind of triggering. So suppose that this is the waveforms. Okay, in here. This is the waveforms, okay, and we have the flat amplitude trigger. So if the amplitude trigger is set here and the waveform is below this, there is no triggering, okay. But if it is above it, then it will trigger. Okay, it's very simple, isn't it? Okay, and then this is a little bit more advanced in that you have an envelope. Okay, and you can set the sensitivity of the envelope. Whenever it breaches the envelope, then it will be triggered and then it will capture. Okay. Now here, again, the waveforms that I show you are voltage waveforms. Okay, they are current waveform as well. Okay, now therefore you should be cognizant into which one you want to trigger based on the voltage or based on the current, or based on the phase voltage or based on the neutral voltage, and so on. Okay, so there are settings that you can do. So depending on the data that you try, the things that you are trying to study, then you should be setting it carefully. Now, suppose that, okay, we are averse to missing something. We don't want to miss out anything. And then you want to have a continuous data monitor. Okay, let's suppose that we have this scenario in here that one cycle is sampled 515 times, okay? So you have 515 samples per cycle, and let's assume that one sample needs 2 bytes, okay? And then at the end, for 1 hour, okay, you will have about 221 megabyte, okay? And then here, in 1 hour, okay, now let's suppose that you have voltage waveform for phase A, B, C, and neutral. So 4 channels, plus current, A, B, C, and then your neutral current. So you have 8 channels total. So in 8 channels total, you will have about 1.8 gigabyte, okay, per hour coming in, okay? So whether that's a lot or not depends on your, what you want to do, right, okay? You want to watch movie, how many gigabyte that is, okay? So compare it. Now you can have a comparison, okay? How many movie is being downloaded, okay? Now in here, so this is a simple monitoring concepts, okay? Again, you see this is the distribution bus, and then let's suppose that this is like in an urban area where from one transformer it feeds 4 feeders. From these 4 feeders, you can see that there are at least 4 PQ monitor in here, another PQ monitor. And then you have power quality monitors located at the customer service entrance as well. So you may end up with 10 monitors. So you can imagine if you have 10 monitors, how much data that you're going to have. It's going to be a lot. Even, so most of the people in the industry, they don't use this continuous data monitoring. What they do is that they use disturbance monitoring mode, okay? Even that, the amount of data that comes in are a lot, okay? So it could be in the gigabyte level, okay, on a daily basis. Okay, so now, okay, so those are the So that is my world, okay? Those are, I work with the data, and then I need to know about where they are located, how they are measured, how they are located, where they are located, okay, the system they live in, okay? Now, the job is that after you receive all of this data, what do you do with that, okay? So over the years, okay, of course there are many concepts of analytics, but the concept that I have used so far is that it is a rigorous applications and exploitation of power quality big data. And the purpose of that is always get the data, turn it into some kind of knowledge. That is the end products, okay? But the question is that how do you do that, okay? In the past, okay, I think until now also, I think most practitioner and application is that you really only take the data, okay, the data. So meaning that these are the voltage measurement data, current measurement data, RMS measurement, frequency, and all sort of measurement, okay? And then you bring them into the knowledge, okay? But what I have been trying to do is also now to modify this approach to include circuit models, okay? So it's not only just using the big data itself, but I also try to incorporate this data plus the circuit models, plus the circuit conditions, plus the system condition, so that I can have a more accurate representation of the knowledge, okay? Because if you just use the data, the measurement data alone, you are probably not using other sets of information that is available to you, okay? So, so now, what I'm going to show you, okay, I think I'll show you two applications, okay? Health monitoring, capacitor banks, and then the other one is detecting incipient cable faults and estimating their locations before the fault happens, actually, okay? And then this is the general approach, okay? Suppose that we are developing applications for detecting health condition of capacitor banks, okay, suppose. So that is sort of the knowledge, the ultimate target. We want to know whether the capacitor is healthy or unhealthy based on some criteria, okay, so that is. So it means in order to be able to do that job, first of all, you have to pick up all the data that have to do with capacitor energizing or capacitor de-energizing. You do not need to know about maybe you don't need to know about fault conditions, okay, or you don't need to know about load energizing. All the data that you really are interested are all that have to do with capacitor energizing, okay, so you narrow down your search. So from here, so usually what happens is that we begin from here, okay, so it means that the first thing to do is that we will have to develop algorithm to detect capacitor energizing. Okay, so suppose that your power quality monitors are located right here, which are most of the time they are located at the feeder head. Okay, so this feeder head monitor will see all kind of disturbances. Okay, so you have to remove all of them, but only keep those that are related to capacitor switching. So the first thing that you have to develop is algorithms that are robust to detect all events that have to do with capacitor energizing, okay? So it means that from here, your first knowledge in here is that whether it is a capacitor energizing or it is not a capacitor energizing. Do you follow me? So that is the first thing that you have to do. And then from there, you go back to the starting point. So it means that you only want to select data that have to do with that, meaning that only waveform data. You don't need to know about the RMS data because it's not useful to you. You know what I meant by RMS data. It's just a flat profile, okay? It's not very useful. So it means that from here you are going to have to remove some outliers, okay? You have, because after you work with real data, you will see that many of them are actually irrelevant. You only need to pick those that are really useful for your purpose. Otherwise, they will just there to confuse you, to degrade your algorithm performance and all that. So selecting the data sets are very, very important. So this is like a very defensive type of development algorithm, okay? So you only want to select maybe waveform data and maybe sometimes harmonics, okay? But then the reasons why do you need to choose harmonics data? Okay, and this is where the system knowledge comes to play, because when you energize capacitor bank, okay, it may actually move the system resonant condition closer to the point where it will resonate with other circuits. Okay, so therefore in here, this could be the first successful steps. Okay, if you choose a wrong data sets, then your algorithm will have low performance. Okay, most likely. And then from there, you select, suppose that you select waveforms, okay? And then, so now you are looking at the right things, okay? So I tend to draw an analogy at this step. It's like, suppose that I am in Tempe here, okay? And then I want to come from my hotel to this place, okay? But I use a wrong map. I use a Chicago map. I will never get to here. Is that right? Okay. So if I am not using waveforms, I'm using RMS, most likely I will never get to my destination. You follow me? So this one here is very critical. And then from there, okay, the next thing is that what do you want to do? What do you have to do with the waveforms? Okay. So this is where the insights from human engineers are very important, because when you present the waveform data to them, ask them, okay, what do you think of this? Why do you think it is a capacitor switching? What makes you think it is this disturbance or that disturbance? Okay, and they will teach you, okay, about this and that and this and that. And then you're seeing that maybe it's a pretty hazy, but eventually you are going to draw some conclusion and you'll be able. And then you can study on your own textbook as well, right? Okay, so this is time frequency. So maybe you will transform all of this data into some unique features. Okay, maybe it is a time in time domain, in frequency domain, or in phase domain, or in wavelet domains. Okay, to look at the smoothness of the waveforms. Okay, and then from here you may end up with some pieces of information that are floating around, okay? And this is the time where you probably can interject it with system models, okay? Suppose that you want to look at the health condition of the circuit switcher, okay? So you can have a functional model of the circuit switcher in here, or actually you have a physical model of that, okay? And insert it into here. And then you will have some kind of algorithm in here to combine all of this information and then mold it into something that is interpretable, okay, that you can explain why your answer is capacitor energizing and not other things. Okay, so this is a process coming down to here, okay, and then suppose the answer is that yes, it is capacitor bank. Now, most power engineers are very interested to know why. When you say capacitor energizing, they want to know why do you think it's capacitor energizing. Give me some evidence that it is capacitor energizing. Okay, and then you'll be able to trace back, okay, or it is a capacitor energizing because the voltage is at this level, the frequency is here, the duration is here, and so on and so on. Therefore, I think with confidence level of 90%, it is capacitor energizing. So it is, you can trace it back. Now, as opposed that if you give a answer that is, oh, it's a line energizing, okay, and the answer is obviously wrong, right? Okay, then you can still trace back why it's wrong, where it makes the mistake, and then you go into that part, okay, maybe your duration is not right, the way that you extract the duration, you will fix that and then come back, and eventually you'll get the right answer. So you are including the human knowledge into all of this process, okay? So this is the approximate process that I usually try to do, try to mimic the thought process of an engineer, okay? Now, okay, so this is the first application of that, okay? You can see that in this particular one in here, this is a capacitor energizing, but distribution capacitor banks, I'm only focusing on distribution capacitor banks for now. I'll have an example on transmission capacitor, okay? So for this one in here, what I am interested in here is the system impact of energizing. So when you energize a capacitor, how does it impact the the distribution circuits from the perspective of voltage transients, how high the voltage transient can go. Okay, what is the transient frequency, how close it is to harmonic resonance. Okay, and what is the increase in THD, and then what is the reactive power contribution. Okay, whether it will push the system into overcompensations or extreme undercompensation, but closer to 1, or how, okay? And then we want to look at the health condition of the capacitor units in here, and and then we want to look at the health condition of the circuit switcher, okay? And this is an example of a distribution capacitor. I'm sure you have seen that. And so this is like for one phase. For one phase, you may have 2 units, okay? So in here, 1 unit may be like 100 kVAR, so you may have a 600 kVAR bang in right here, and it varies, okay? And now, so this is an example, okay? So I have shown you the big picture of the approach, but I don't fill in the algorithm for the for each block, okay? You can find it in papers that have been published over the years. So this is an actual measurement. So when you look at this, okay, this is measured at this peak voltage here is about 20,000 volt, 20 kilovolts. So I think this is about maybe 12.47 kV distribution feeder probably, okay? We have to work out the number. And then you can see that there's energizing in here. So remember that in here, the monitor is located right here. So it means this monitor is going to see all sort of disturbance events. So the first thing is that I have to make sure that the event is capacitor energizing, okay? Now, so this is the results of the algorithms, okay? So first, the algorithm will go into the waveforms, okay? And then see that whether it is a capacitor switching event or it is not, okay? So apparently it shows you that this is a capacitor switching event, okay? But it is not capable of telling you whether it is a normal energizing or a successful de-energizing or a restrike and opening. So that's why this is an OR in here, an OR in here. And then after some analysis, it will tell you that it is a normal energizing, okay? And then it tells you that the bang is downstream from the power quality monitor, okay? So it can tell you the relative location as well. In some cases, you might have a power quality monitor that is installed midline. Therefore, some capacitor bang will appear as upstream from the monitoring location. Okay, and then it can tell you also that this analysis in here has a high confidence. Okay, the results is with 90% or higher probability that this is correct answer. Then it will start showing you the evidence in here, why it thinks. So it will look at the resonant frequency, okay? That most likely the resonant frequency is going to be 280 hertz. Okay, there is no evidence of resonance because you can see there are some distortion here, but the distortion before and after it happens are approximately similar, maybe increased by 0.5% or so. So there is no evidence of increase in distortion. And then it looked into capacitor unit health conditions, okay? So you remember there are 2 units, okay? And then if the capacitor is energized properly, both units has to come online at the same amount, okay? And then it estimates that the each phase supply contributes about 2200 kVAR, 2200 kVAR, 2200 kVAR in here. And then the total is about 6.6400 kVAR. And then it says that the increase is balanced, okay? And then it is capacitor is energized. To this point, it says it's closing or de-energizing, okay? But here, after looking at these numbers, okay, it's actually energized. Okay, and then for the performance of the circuit switcher now, when you look at the circuit switcher, you can see that the waveform here is pretty much smooth immediately after the energizing. You don't see any restrike conditions, okay? Therefore, the circuit switcher declares that there is no restrikes during closing in any phase, okay? Because this is a closing event, so it will tell you whether during the closing there is a pre-strike or not, because sometimes when the switch is closing like this, most of these are electromechanical switch. Therefore, having the knowledge of the type of the switch is very clear. When it is moving close enough, okay, it doesn't have to mate before the current flow. Actually, when it comes closer, there will be arc jumping across from one side to another side, okay? That's why you can see that in many of these switching, you will see that it happens at the voltage peak, okay? Because at the voltage peak, that is the most likely phase where the arc will jump from one blade to another blade, okay? So that is what I meant by having the circuit models or the device model embedded, okay, in some form is important. Now, and then it can tell you also about whether there is a closing control or no closing control. In this particular case, the capacitor, because it is overhead capacitor bank, there is no synchronous closing control. Okay, that's why you can see this is minus 90 degree, which is matching this phase A in here, minus 90 degree. Okay, now, so this is one example, and then this is also another example. You can see that too, that this one here, that this is also telling you about the same thing, giving you another example, except that the resonance is 520. Okay, and then in here, I forgot to mention that in here, this algorithm is also capable of estimating the distance between the monitoring location down to the capacitor. It tells you that this is about 3 miles or so, 2.9 to 3.739 miles, because it's energizing, therefore it can be estimated. Likewise, this one too, I can tell that this is between 1.58 to 1.8 miles. Okay, now the next thing is that, so what do you think of these waveforms? This is capacitor energizing, okay, capacitor energizing waveforms, and then you can see then that this one here has a restrike during opening. Okay, it can tell you this is a restrike during opening, because in this particular one, that the switch has already opened, okay, but then because of some contaminants on the blades, okay, as it is moving opening, the arc, as it passes to zero crossing, the arc is extinguished, but then as it approaches the peak voltage, the arc jump across again. It doesn't mean that the blade like doing this, but it's simply that the arc is re-established. That's why you can see that in here that it happens right here near the peak in here. Okay, so the energizing waveform should not see this type of restrike. So there are 2 restrikes in here, 2 or more restrikes. It can tell you the peak voltage, and then it can tell you also that the capacitor is de-energized. You can see that these are the negative number in here. Okay, so it's actually a 3 megafarad capacitor being de-energized. Now, using this one, you can see that that is not a capacitor switching, therefore the waveforms, the analytics will tell you it is not. Okay, and moving on, this is also not, although it looks pretty similar at the beginning in here. Do I have many? Okay, so now transmission capacitor banks. Okay, so the difficult part on the distribution circuit is that you have so many equipment being energized in here, whether it's load or so you have to discriminate. Yes, now go ahead.
Are we allowed to ask questions now or at the end?
I'm okay. I stay okay with you.
May I know what you use to simulate these scenarios? In the sense you are talking about the mechanical arc jumping and everything. What do you use to actually study this?
So all of these are not simulation. All of these are real world. Okay, all of these are real world. Okay, so how do I know that it is the switch? Because I really go into the switch, and then look at the mechanism. It's a electromechanical switch. Okay, and then you look at the physics of the switch, how they are, how the arc current is established, how the arc current is extinguished, and then from there you can see the manifestation in voltage and current. Actually, you can really see that in the current. Okay.
So you only use voltage and current to derive these all analysis. Right?
Yes, derive all of this analysis.
Especially when the downstream and the upstream part?
It's also using the voltage analysis. Voltage and current analysis. Okay, based on the first derivative of the switching instant of the transients. Okay, so that can only be done if you have sufficient number of samples per cycle, like 256 and higher. If it is measured using protective relay, which is maybe 32 or 64 samples, you probably cannot get that. Okay, this one, okay, now, any other questions? All right, so this one here is a different application. This one here is still capacitor banks, okay, but our interest now is just looking at the health condition of the circuit switcher. Okay, of course, I'm also interested in the health condition of the capacitor units, but I don't show it here. I'm only showing the health condition of the circuit switcher. Now because transmission capacitor bank are much larger than distribution, it is probably like 30 megafarad or higher. Okay, and then in one substation there can be multiple capacitors. Okay, so for example in here, so you can see this is a typical configuration of substation, transmission level capacitor. You can see this is the capacitor rack. Okay, you have phase A and B and C. Okay, in each phase you can see there are row and rows of capacitor in here. So each capacitor units could be protected externally or internally by fuse. Okay, and then you have this arrestor. I think you know what is there. Inrush current limiting reactor. You have a ground switch. Okay, and you have a circuit breaker. And circuit breaker. People don't really use circuit breaker these days. Most of them use circuit switcher, okay? Circuit switcher to energize or de-energize capacitor bank. So so this is like the circuit switcher in here, and then you might have a circuit breaker behind it, okay? Now, so this is an actual view of a transmission capacitor. Now you can see that in this particular application in here, in this one line diagram, you have a 161 kV capacitor bank bus, and then this capacitor bus here has three banks. Bank number 1, bank number 2, bank number 3, like that. Okay, and then the power quality monitors is measuring the voltage right here at the bus, and the current is measured right here. Okay, so and then this is the circuit switcher right here, right there. Okay, and this is a simplified view of that. Okay, so what we are after in this view is that we want to assess the health condition of the capacitor circuit switcher. Okay, now if you have been working around with capacitor bank quite some time, you would know that capacitor can be energized with circuit switcher that have no control. It's just close energized, but they can be also energized using pre-insertion element, okay, such as this one that I'm talking about. It can be also energized using synchronous closing control, which is another strategy. But let's look at this one first, okay? So in here you can see that this is the capacitor, one of the capacitor, and let's assume that in that bank there is no other capacitor that is online at this moment. So our job is that we want to energize this, but the way that we energize here is that we want to minimize the transients and also the inrush current. So the way that it works is that we want to switch into here, such as this, okay, so that the current flows through here and then going down to here. Therefore you minimize the transients. But then after that you don't want to leave it there, because if you leave it there you are going to cause some losses in this configuration, in this capacitor. So you have to bypass it, okay? So the mechanism, how it works is that you have an arm that looks like this, that is moving across like that. So it will move in here, touch this, and then move away. Okay, guess how fast this is? It has to be completed within 4 to 8 cycles. Okay, if you just think that the middle point, 6 cycle is 1/10 of a second, right? 1/10 of a second. Okay, so in 100 milliseconds. So you cannot even see like that. Okay, so the goal here is to figure out whether there is a misalignment. If there is a misalignment, okay, the arm maybe swing immediately and arrive direct here bypassing this one. It doesn't even stop at RL branch, okay? Or it may swing and then stuck in here, okay? Or another problem is that one of these has has been damaged. There is some damage into it. So the idea is to figure out what is going on in here. So our goal here is to figure out the switch in and switch out time. Okay, what is the speed of the insertion in here? Okay, and then what is the R and L? So if we can estimate the R and L, then that will be good. Okay, so this is one arrangement. So you can see that in here initially this is the voltage measurement at 161 kV line to line, and then no capacitor bank is available in service right now. So the condition is like this. Now when it is energized like this, this is the manifestation in voltage and current. Okay, and then immediately gone to here. So immediately in here, do you see any transient in here? This thing happened between here and here. This one, the time is this one here. Here, it's somewhere here, 6 cycles later. You don't see anything, right, with your eyes? Okay? Okay, so this is one. So, but it does happen right here. Okay, somewhere there. Now, the next one. Okay, the next one have to do with one capacitor bank. One or more are already in service. So there are current already in here. So the current is flowing through here. Okay, and then this capacitor now is energized. Okay, the second one coming in, and then that's why you see this. Okay, and then after that it's bypass. Now you can see that there's supposed to be some transient, but you don't see it there. Okay, because well, it's not supposed to be there because it's so smooth now. Okay, now look at this one then. Okay, look at this one. The current is here about 100 amps peak, and then after that about 100 amp peaks. Okay, so is this capacitor energizing or is not capacitor energizing? If you don't know the systems, then you probably take that into account and then use it in your algorithm development. Well, this is what I call the sympathetic transients. There is another capacitor bank nearby, okay, that is energized, and then it is coupled into the other capacitor. That's why you see only this, but you don't see anything energized physically in here. So again, the objective here is to flag abnormal energizing. Okay, whether there is a missing pre-insertion or failed switch out. Okay, it's stuck. Okay, detect this as I described before. Now let me just show you the results. Okay, in the interest of time. Okay, and then the circuit switcher in here has many. There are 4 capacitor banks in this particular example. Okay, and then the reactance is 15 ohms and the resistance is 5 ohms for the first 3 switch, and the last one has 81. Now you can see that going through all of this, these are the step-by-step analysis like an engineer would calculate the impedances and so on. Okay, so it derives all of this. Okay, and then finally it comes up with the switch out duration. Okay, you can see that the switch out duration here is 7.23 cycle, 6.87 cycles, so it's within the range. Okay, within this range. But then in this particular case here, the algorithm is not capable of extracting the resistance, which is 5 ohms. It's not capable. So it says rather than give you a wrong number, because in each of these there is a test of confidence. Okay, then if the confidence is below my satisfaction, that it will be declared as negative 999. Okay, 99.99. And then the step change, which is this reactance in here, you can see that the reactance about 13 ohms. Okay, so and they're all about 13 ohms. Okay, so this one is actually behaving as normal, the circuit switcher. Okay, now this one here is coming from another substation also. Okay, you can see that in this particular case here, I was able to capture the resistance of 81 ohms about here. Okay, and the step change of reactance about 15 ohms in here. Okay, and the switch out duration is about 6 cycles as well. Okay, so in here we detect a lot of this, and then we have the measurement for a few weeks, and then to determine this, for this particular, it's just 2 weeks of measurement. We can see that the impedance is roughly about 15 ohms in here, and then there are some that is that do not have pre-insertion elements. That's why it is 0 in here. Okay, we test it out whether it will pick up those that are not that do not have pre-insertion or not. And then in here you can see that we have the confidence interval in here and in here. Now you can see that the spread in here. So this is really within the what we expect should be. If there is a missing or damaged element, this data point would be shooting up very high, okay? Or the duration would be maybe infinity, okay? Instead of 6 cycles, it may be beyond some cycles, which is forever then, okay? So that is, this is the duration that you can see that. This is the duration between 4 to 10 cycles. I mean, up to here, some are 9 cycles also, okay? So this is the way that was developed, okay? Now, this is, I'm also going through this pretty quickly, all right? Any questions? Okay, so incipient cable faults, okay? So these are the these are the faults that are developing. It is not a full-blown fault yet, okay? There are many things that we'd like to find out. So first is to detect incipient faults, and then after that determine the root cause of the cable failure, whether the failure is on the insulation along the cable, the body of the cable, or at the termination or the joint and splice. And most of the time the failures really happen at the splice, okay? Because that seems to be the weakest link. And then what we like to do also to estimate the distance to the incipient faults, the faults that is still developing, okay? So I will show you the first one and the last one, not the one in the middle, okay? Now, so this is, all of these are real data again, okay? You can see that the monitor is at the feeder head, and then a portion of the feeder here are actually overhead, okay, overhead lines, okay? And some portions are here and are the cables, okay? Now, so this is how it happens that in some disturbances, you will see that, so this is again the voltage, this is the current. Now you can see that there is current, there is a fault in here, jumping only a quarter of a cycle from here, jumping here and up like that, okay? And then it disappears, okay? And then protective relay upstream will not typically see this type of faults because it self-clears so fast. The only thing that it sees is the voltage wave-shape fault in here, okay? But then when you look at this waveform for the first time, you might be misled that actually the information to capture or to identify the faults may be located at the voltage waveform, when you see that, it is not true, because actually the trigger, okay, the root cause is actually coming from the current. The current interact with the impedance, giving rise to the voltage disturbance. That's what happens. So we need to know the phenomena. We need to know the theory, the circuit theory, how the disturbance happens. But so if you're just looking at the waveform itself, okay, you may be ending up in Chicago, okay, instead of in Tempe here, okay? So, so this happens like this, our 1940, okay? And then it happens about 2 hours later. The same phase B happens here. And then 2 days later, it turns into a full-blown fault, okay? And then the relay now will open, okay? So the goal is that before it turns into this type of full-blown faults, we want to capture it. We want to detect it. And not only detect it, we want to figure out where that is, where the fault happens along the cable. Okay? Now, so this is an example. Okay, this one, you can see that there is one here. Okay? And then 10 seconds later, another one happens here. So this is phase A. And then another one later, this is 2 minutes later. Okay? So the way that it progresses, I mean, we tend to say that it happens at the increasing frequency. It happens like maybe every week, and then every few days, every hour, minutes, and then finally it blows. It's not that clean, okay? It can happen like 10 seconds and then 2 minutes later, okay? We never know. It's like almost random, okay? But therefore, the algorithm has to be very, very robust, okay? So let me show you some of this quickly. So you can see that this is the fault point. Sometimes only a quarter of a cycle, okay? Sometimes there are half a cycle happening here, but nothing happened before. So this represents a good opportunity for us to detect it before it actually happens. Some are actually 1 cycle, but it doesn't cause full-blown faults. Some are actually 2 1 cycle. You can see that, okay? Now, and then this one, some are 1.5 cycle. Some are multiple, okay, coming in like here, here. Okay, so this is a simple algorithms, okay? That is, basically it's just a signal processing, okay? Now you can see that in here, this tells you that number of incipient faults, only 1 in here, okay? And then another one here, there are 2 incipient faults. Where? There are 2 here, 2 or more, okay? And then in here, there are 2 also, okay? 2 and 2 in here. So there are 2 incipient faults. Detect all of this, and so on, okay? And then it can tell you also that this is not an incipient cable fault because this is an actual full-blown fault. So the previous part that I showed you is not very difficult to develop, okay? But the most difficult one is to figure out where the fault is, okay? So what we want to do is to figure out when this fault happens like this, where is the location of the fault? Okay, can it be actually done? Okay, we doubt ourselves whether we can ever do that. Okay, and apparently we do. We finally have that happen. Okay, and the key goal here is that we need to predict, we need to estimate the arc voltage. Okay, so you can see that the monitor is at the substation. Okay, and the fault is somewhere along the line under the cable. So what the monitor sees the voltage and the current at the substation, not at the fault point. You follow me? Okay, so you will have to have an estimation made so that as if you have a monitor in front of the fault, and then you will estimate what is the voltage at the fault point. That is the arc voltage, okay? And what is that current? Because the current that you see at the substation, the fault current combined with the load current and everything else. So you have to have an algorithm essentially moving that monitor, drop it at the fault points. And what do you see right there? Okay? Then from there you can estimate the arc voltage. Okay? And using the arc voltage and the impedance that you estimated, you can get a estimate that it is actually 0.38 ohms to 0.72 ohms. Okay? And then in here also, so this is the incipient faults, okay, happening at this time in here, and then happening a few minutes cycles later, okay, and then we estimate it. So you can see if you remember the number, okay, from here this is 0.38 to 0.7, this is also 0.35 to 0.7 approximately, and this is when the full-blown faults happen. Okay, when the full-blown faults happen, it is not difficult to estimate the fault location. We estimated that it is about 0.48 ohms, okay, which is very well within that initial estimates, okay. So this is rather successful. It doesn't work all the time. It works only when you have high quality of monitoring device, where the sample is number of samples per cycle is like 512 samples per cycle. If the number of samples drop to 128, you probably won't get it. Okay, and you can see that this one too. In this particular one in here, you can see that the incipient faults happen very quickly, right here, right here, right here, and then it turns into a full-blown faults right here. Okay, and you can see that using this estimate, we were able to, using this approach, we were able to estimate that the fault location is actually at 1.38, 1.2, 1.15. So it is pretty stable, okay? Well, we tend to think that, that this is not good results because the number are not matching. We're expecting this is 1.3789, and then this is 1.3791, 1.3712. Then we say, oh, it's a good match. No, okay, it doesn't have to be like that. Okay, because when we are talking about cable faults, okay, what we really want to get is the distance between two main holes. Because as long as your estimates are accurate within one or two main holes, that is where the line crew, okay, go into the main hole and then fix that portions. Okay, you don't have to go to the accuracy of however many feet, 10 feet or so. As long as from one main hole to another main hole, which is typically 500 feet, that is good enough for them. Okay, because when they replace, they don't replace that part like 1 foot long cable. They replace like some span of it. Okay, so this is my last slides. Okay, go ahead.
Professor, so how do you segregate the fault information from the waveform data?
Fault information?
Virtually moving the PQ meter to...
Yes, okay. So,
because we don't, system can have so many things happening, maybe regulator switching, capacitor switching,
yes,
transformer,
that is, yes,
PV panels.
that is the very first thing that you have to do. That is the very beginning and the data selections. Okay, so that's why in all of these waveforms, okay, typically when it is triggered, okay, there are 2 or 3 cycles before the event, before the transients, and you will want to use that short period of measurements, okay, to extract whatever you want to exclude. Okay, use that as your reference. Okay, and then the one that is in the middle, okay, then you want to remove the contribution from the loads from other switching. Okay, and then also sometimes you can see those waveform that is after that, and you may be able to use that as well. Okay, but because you only have like 12 cycles to work with. Okay. Okay. Any questions? Other questions?
I have a question. So when you were talking about the last few, because at the beginning I think at page 15 you talk about the estimation of the distance, and then towards the end you explain how actually do the very nice estimation of where the event is happening. So I would like to know, you talk about something about 128 and then 500 samples. You say, oh, when it's getting lower than certain resolution, then you actually cannot capture.
Mm-hmm.
So is there any magic number in between that is defining the threshold, or this is empirical result that people typically can hardly see?
Okay, it depends also
Right.
on your budget.
Okay.
Okay, usually 256 is like the standard as of a few years ago. 256, you want it at least 256. But what I have worked with, data that I have worked with are mostly 512. 512 samples. I will be able to get more accurate information out from with 512. You can imagine that 512 sample points per cycle. It depends on the phenomena that you are analyzing. If you're looking at the very high frequency things, okay, then maybe that's not enough. So you may want to have like 1,024 samples per cycle, like that. So I would say that the minimum would be 256 for anything that is reasonable to do. But higher the better. 512 is probably the next step. Okay, and then there are all kinds of power quality monitors these days that are increasingly smarter and smarter. They can also do adaptive sampling rate. Okay, so they can sample it and then capture it at a high sampling rate and then do a downsampling. If the waveform doesn't contain any high frequency, they do the downsampling. And they have other mechanism as well. And the last one, the recent trend is that all the power quality monitors, they want it to make it as if it is like a synchronized waveform measurements, similar to PMU. So PMU is not waveform, it's just like a voltage and angle quantity, whereas this one is the waveforms they want to synchronize. Okay, I'm not sure how it will turn out. Questions?
I guess I was going to ask that if power quality monitors can be time synchronized. And
Yes.
if you have looked at any data, like for example, studying one event from multiple monitors.
Yes.
And if you
Yes. So time synchronized, you will be okay. For now, okay. Sometimes I do need to have multiple measurement from multiple power quality monitors, okay? And I know by looking at this transient, they should happen at the same time, but they are not. So what I do is that I have to manually synchronize them, adjust, okay? And then from there, I reset the timing, the timestamp for all other events. So it is more problem for me, and I may get it wrong, you know. Therefore, if it's already time synchronized, okay, suppose for capacitor bank, supposedly, okay, you energize capacitor banks, okay, and there is a monitor to capture the waveform, but there is a relay also protecting the capacitor bank, and they have their own set of measurements, okay, and these two ideally should be synchronized, and they can be captured by power quality monitor as well. So by combining the waveform from the capacitor energizing event, and by reading the relay data that are synchronized with the capacitor bank event, then analysis would be more accurate. Okay, there is a real need on that one. In the past, before the invention of GPS clock, it was a lot more difficult because you have to synchronize it on your own. Okay, you have to have some kind of reference that you guess on your own, so it's not really true. Okay. Any questions?
Any questions? Yeah, I have a question.
Okay.
So I saw some of the results you have like confidence zone, confidence level, the decision making, which I feel very good. I'm wondering, is there any probability model behind that for the decision making?
I think yes, it should. I would say yes. It should be. You should have some statistical models onto that. Okay, but again, if you have so many data, okay, then you may be able to get that. But sometimes, after monitoring for a few months, you only end up with 100 events, supposedly. Okay, and then for that, you may not be able to create a model. So you will have to, like, how many times, you will want to work with the utility engineers, like whether this number is reasonable or not, okay? And then from there, you can develop an ad hoc or an experimental basis type of confidence, okay? Early on, I show you that we can extract multiple features from the waveforms, okay? And then what I use to combine them together is using rule-based method, very simple rule-based method. But once you have like hitting like 20, 30 rules, okay, you will soon figure out that some rules are conflicting with one another, okay? So you have to have a resolution conflict, okay, conflict resolution algorithm. And then after you have enough data coming in, you analyze how often the rules are used, okay? And then you can probably remove some of the rules that you initially think that are important, and now suddenly it has never been triggered, it has never been used, so you just want to remove them. Or if the rules are used more and more often, then that rules becomes more prominent. Therefore, you want to increase the confidence level based on that rules. Okay, eventually it will show up like that. But how do you know about this? I mean, you have to, for every result, you always have to go back and make sure where it lies in the range of the events like that. Okay?
Okay. Yeah, let's thank the speaker. Yeah.
Thank you, everyone.